Sumera, you got the probe?
Yes, it is on the way, sir. Dr. Athiya is bringing the probe, and we will be able to show it in 15 to 20 minutes, sir. But I have, sir, NMR sample tube and the spinner and a depth gauge.
Okay, Sumera, why we need to spin the sample?
So that the solubility and the sample will remain homogeneous, and it will be, if it is soluble, it will remain continuously moving. It will ensure the homogeneity of your magnetic field.
Okay, so this is what we were trying to discuss the last time, that the simplest thing which you can do with pulse NMR spectroscopy is that you have your bulk magnetization vector, which is called net magnetization,
Right.
and then you give a 90x pulse, you bring that magnetization vector on XY plane, and then you turn on the detector, and the detector will see various resonance frequencies belonging to various kinds of protons. For instance, in this case, you can see free induction decay, time domain signal of two different resonances, So you see two different resonances, one at 5 and the other is 7.5 chemical shift. And the free induction decay will eventually is converted into frequency domain by a Fourier transformation, which is a mathematical process. And by this, you get a frequency domain signal.
Sir,
This is what
sir,
yeah,
your sir picture is not clear. We cannot see you with clearly.
slides आपको नजर नहीं आ रही है?
Sir, we can see the slide, but video is not clear.
So Mera, who cares? I'm not that photogenic, don't worry.
Okay.
Okay, so he's trying to fix. I think he would be able to fix it in a few minutes. So okay, so this is eventually if you have many frequencies, which you can see down the free induction decay, then the FID looks horrible. It's cumulative FIDs of as many protons or carbons or whatever the elements are, and then you see a pattern like this, and this is the kind of a free induction decay time domain. So you see, this is a time scale in which these frequencies, resonance frequencies or Larmor frequencies, eventually these signals go up and relaxation takes place. So during this process of relaxation, free induction decays are recorded by detector. I told you that these are non-radiative, that there is no radiation which is recorded. It's only that these magnetization vectors on XY plane moving in a circular motion, and when they pass through in front of the detector coil, you see a positive signal. When they are away, then you see a negative signal. And then at the same time, they're also losing the angle because they are trying to achieve thermal equilibrium. And I told you that there are two mechanisms through which relaxation takes place. One is called T1, big T1, spin lattice relaxation, where energy which you have given through a radio frequency is disseminated, lost to the lattice in the environment, because there are so many other molecules present, such as solvents, and eventually this energy goes to it. It's about 65% of energy is lost predominantly by T1 mechanism. So this is the predominant mechanism through which relaxation takes place, called T1, the spin lattice relaxation. The other is called spin relaxation, and that is just a energy transfer from one proton to the other in case of proton NMR spectrum. It just dephase the signal, but it doesn't really is an effective mechanism of relaxation or losing the energy. So actually what we are interested in is T1 relaxation, and as I'm going to tell you the subsequent experiment how T1 is calculated. Okay, so this is what eventually you get by pulse NMR spectrum, FID of a molecule like this, which has broadly three different types of protons, will give you three different types of signals, because there are three FITs which are converted by FT Fourier transformation, and you get three frequency domain signals. So this is the classical NMR spectrum, which you get out of a single pulse experiment. And I told you that pulse Fourier transformation method. Now NMR is, well, pulsed Fourier transformation NMR spectroscopy, or PFT NMR spectroscopy. And uh, this is what we have discussed last time also, that the pulse Fourier transformation and mass spectroscopy is very different from classical or continuous wave NMR spectroscopy, where you just simply record absorption and you don't need to understand anything from vector diagram to pulses, nothing, but a just simple absorption of radio frequency as it matches with the Larmor frequency of various protons, you get the signal, and that's it. So for that kind of simple continuous wave NMR spectroscopy, you do not really need to understand vector diagram, but that is just obsolete, gone. This is past, because it doesn't explain the modern NMR spectroscopy. In order to understand modern NMR spectroscopy technique, you must understand pulses, you must understand log vector diagrams, you must understand FID and Fourier transformation. वो कह रहे हैं कि पिक्चर क्लियर नहीं है। ये लेक्चर की सर या आपकी? Maybe. Okay, so and then how pulse Fourier transmission is spectroscopy contribute, that we have discussed last time, that increased signal to noise ratio, because it's just a very simple phenomena. You have bulk magnetization vector M naught, which is a collective net magnetization Boltzmann distribution axis of various protons, and then you give a 90x pulse perpendicular, and then you bring it to Y. You turn off the radio frequency pulse, you turn on the detector, it records free induction decay, you do a Fourier transformation, and that just takes only a few seconds. After some time, you do exactly the same thing, because by that time it has relaxed back to thermal equilibrium, and then you get, so you can repeat this experiment literally hundreds of times. And as you repeat this experiment hundreds of times, you get lots of FIDs, you convert them into frequency domain, and you get better to signal to noise ratio, which is also called sensitivity. Can you see me clearly now? Sumera and Hina?
No, sir, we cannot see you clearly. Sir, we cannot see you clearly still.
Okay.
So there's your camera is blurred. We can see only slides.
Uh, Dr. Kia,
Yes,
till
sir.
fix the problem, can you kindly explain what is signal to noise ratio or sensitivity?
Sir, as you mentioned in your previous lecture, that signals are always overlapping. So, for example, you probably most of you have run proton NMR experiment, and in which you usually give like 16 or 32 or 64 or 128 number of scans. So these number of scans are actually number of experiments. So each scan is one experiment. And when you run these experiments, so it means you are increasing the number of scans, so you're increasing the number of experiments. The signals are overlapped. So that is why when you increase number of scans, so signals overlap, but there are noises, and you could see in your baseline that your baseline getting thinner and thinner. That is noises. So that means that the noises are random, so they cannot overlap. So with the increasing number of experiments, signals overlap and you get very sharp, intense peaks, while your baseline get thinner and thinner. So this is what signal to noise ratio. With the signals are overlapping and noises are random, so they just cancel out each other.
Wonderful, thank you very much. And I hope that you can see me now.
Yes, sir.
Happy?
Yes, sir.
Okay. Okay, so let's discuss the simplest pulse NMR experiment. Simplest pulse NMR experiment. And that is something very exciting. So the simplest pulse NMR experiment is represented in two different ways. On top of it, this one, can you see the arrow? Can you see the arrow which I'm
Yes,
trying?
yes, sir.
Okay.
We can see that.
Okay, so in modern NMR spectroscopy, the pulse sequences are presented in diagrams like this. So, you give a relaxation time, you give a 90x pulse. So turn on the pulse, turn off the pulse, wait for a while, it becomes decoherent, turn on the detector, you get free induction decay, FID, as many FID as the protons. If there are three different types of protons, there are three different types of FIDs. If there are 2,000 different types of protons, such as in proteins, then you get 2,000 FIDs. You get a Fourier transformation, FT, you get three different signals. For example, if you have three different protons. Now, after this experiment, you wait for a while, which is called relaxation time. Generally, we give 5T1, and we will tell you how T1 is calculated. So you wait a bit extra time till magnetization vector again become longitudinal magnetization vector. It's called longitudinal magnetization vector towards the direction of Z. Okay, and then you give again a pulse. You bring it to the XY plane, which is called transverse plane. And these transverse magnetization vector, you again record FID. You do a Fourier transformation, you get 3 signals. Okay. Then you wait for a while. It's called relaxation time. Sometimes it's called preparation time. Then this is excitation, this is detection. So preparation means you're preparing. Preparing means that you are actually waiting till it become, fully restored towards longitudinal direction, and then you again give a pulse, you bring it to the XY plane, you turn on the detector, you get FID, you do Fourier transformation, and you get signal. And the same thing is represented by a vector diagram. So this is, the B naught direction, this is the Boltzmann distribution axis, net magnetization, block magnetization vector, longitudinal axis. You give 90 pulse B1, and that you get, this is from the Y, and that doesn't matter. And then it appears that it comes on the XY plane. This is your detector, a little man with telescope, and that monitor the movement of these resonant frequencies on the XY plane till it goes up, and then you record. This is the detector which is recording free induction decay. And it can be any simple NMR. For instance, Dr. Atia said 16 to 32 skein. You get proton NMR spectrum. If you are interested in C13, you get C13 spectrum. The difference is that in case of proton NMR, you have your radio frequency fixed at the uh, resonant frequency of protons. In case of C13, it is a different frequency, and you can be very, very selective that you can detect any of this. So it's the simplest one pulse NMR experiment, the simplest one. And now, there are literally experiment in which you have not one, but thousands of pulses. You just play with that. And if you understand what happened when you give a pulse, where it will go, and then there is also a concept which we will discuss with you. It's called rotating frame of reference, where these vectors are on the XY plane, then you would be able to understand this multi-pulse NMR experiment, which we will discuss later. So information content in simple proton NMR spectrum, chemical shift. You get chemical shift. Chemical shifts, this is what chemists are looking for, because chemical shifts represent chemical environment. It represents microelectronic environment of the protons, and that actually means structure, because if you know which one is shielded, which one is de-shielded, then you can figure out the structure of a molecule, no matter how complex it is, because it's just a matter of understanding which different types of proton in different places. So for instance, in this very simple ethanol spectrum, you can see that there are 3 different signals representing 3 different types of protons. And this is the shielded one, CH3. This is CH2. And this is OH. So you see 3 chemical environment. And you know why they're different? Because there is an oxygen atom, which is electronegative atom, and it can withdraw the electrons, make them de-shielded. The second important information which you get from that is integration. Integration is number of protons under the peak or number of protons of the same chemical and magnetic environment. For instance, in this case, CH3 means 3 protons and CH2 has 2 protons and OH is 1 proton. So you can see this line. Now we don't show lines. Now in proton NMR spectrum, integration is actually written down there as a number, as an integer. But actually this is area under the peak, which represent the number of protons present. So you can see that this line, ascending line, is 3 times this one. And this is, 2 times versus this one. So it can tell you that these are 3 protons versus 2 protons versus 1 proton. And that is spin coupling, very important. Splitting of signal due to coupling with the neighboring protons. And this is what my colleagues will actually define you all 3 concepts: chemical shifts, and spin coupling. Integration is very simple because this is what you get as an integer also. At the time when we didn't really have, a long time ago, when NMR spectrum were not so advanced, people used to cut the peaks by Caesar, and they used to weight it on a superanalytical balance. So the difference in the weight was representative of number of protons. Here you can, by using simulation, you can get integration. Most important is the splitting of signals, which provide you information about the neighboring protons. And this makes NMR extremely powerful technique because it gives you not only the electronic environment, chemical environment, which means the structures, but also, the neighboring protons. For instance, in this case, CH3 is split into 3 peaks due to CH2, right? CH2 is split it into, I don't know, it's got it because 3 plus 1, this is a complex signal. So n plus 1 is going to be 4 plus 1, 5. And that these signals are actually doublet, which my doublet of a doublet, which my colleagues will actually explain to you because it cannot really be simple explanation. They split first because of OH and they further split because of CH3. Okay. And then, of course, OH, which is supposed to be splitted as a triplet, but OH is exchangeable, so this appears as a broad singlet. So, these information you get from the proton NMRs, even from the simplest proton NMR spectrum, you get such information. Now, chemical shifts depends on the inductive effect or resonance effect of attached protons. As you have seen in this case, this OH, the proton here, oxygen, is directly connected to oxygen, and therefore this is the most d-shielded one because electrons have been removed by electronegative effect of oxygen. CH2 is 1 atom away, because you're talking about carbon directly connected to oxygen, but protons are 1 carbon away, 1 atom away. And as a result of it, they appear a bit more shielded, and CH3, which is still far away from oxygen, will appear as a shielded. And now, if I tell you that if we replace this let's say with more electronegative atom, such as fluorine, you know, everything would be more shielded and de-shielded. If it is NH, amine, in that case, you would see, you know, that nitrogen is less electronegative as compared to oxygen, and the chemical shift would be different. So, depending on the electronegativity of attached atom, this is one factor which is explained in this case, inductive or resonance effect. For instance, in case of halogens, you know, uh, if we have fluorine, fluorine is the most elective electronegative one, is going to shield more prominently than chlorine, and then bromine, and then iodine. So if you have fluorine, there's going to be more de-shielded. You have chlorine, it's going to be relatively more de-shielding. If you have bromine, it's less electronegative, it's going to be de-shielded relatively less. And if it is iodine, which is very less electronegative, you would get. So inductive effect, hybridization, sp3 hybridized are more shielded. sp2 hybridized is relatively de-shielded, and sp1 hybridization, sp hybridization is more de-shielded. Magnetic anisotropy in case of pi-electron systems such as alkene, alkyne, benzene, you already know that they have a magnetic anisotropy. They create their own local electronic environment. The benzene protons are more de-shielded as compared to uh, alkene protons because the benzene has a magnetic anisotropy. Hydrogen bonding, if we have a strong hydrogen bonding, you get more de-shielding. If it is less hydrogen bonding, you get a bit shielded. Solvent effect, if you have more polar solvent, the chemical shift will also be affected. So there are many factors, but these are some of the factors. There are many more, but these are five most important factors which affect the chemical shift of protons, even for carbons, even anything, you know, any element which you are trying to detect, uh, the chemical shift of that particular element will be affected because of these factors. Okay. Uh, Anyone would like to discuss this with my colleagues there? Is this clear to everyone?
No one has any question.
So it's appear to be clear. It's okay here. We move forward?
Yes, sir.
Okay. Now we come to a very, very interesting concept. And it's called rotating frame of reference. So, uh, you know, this one, you give a 90 pulse, and then you bring the magnetization vector on XY plane and assume that you have two protons, two different types of proton, such as such as chloroethane or fluoroethane or something like this. Then you have two different vectors moving with a different speed because they have a different Larmor frequency. And remember, these are Larmor frequencies, resonance frequencies. So their movement on XY plane is with the speed of light. Yeah. So if you are outside this frame, you would never be able to understand uh, the movement of these vectors, because they are so fast that you cannot imagine which one is moving faster, the other one, which one is moving slower, because they're already moving with the speed of a light. Okay. So in a stationary frame of reference called laboratory frame, if you're outside this three-dimensional Cartesian, there is no way you can understand the movement of these vectors on XY plane because they are moving the speed of light. Okay. So, in order to make life easy and in order to make mathematics easy, uh, the concept of rotating frame of reference was developed. Uh, and you can see a laboratory frame of reference. Uh, Here you can see that these two are moving with the speed of light, and you don't even know where they are actually. So you can't do anything with them. You will not be able to selectively decouple or move it to manage that direction if you don't know where they are actually. But imagine that if you jump over one of the needle, if you just come and stand on this vector, the other vector will only be moving with a differential velocity. You know, imagine that there are two fast trains moving with a speed of 300 plus. And then if you are standing in a field and you see the trains, you see them moving in front of you, and the speed of these trains are 300. One of them is 300, the other one is 301. So you see them just moving forward. But if you are in that one of the trains, the difference between the velocity of these two trains is only 1 kilometer because you are part of the system. Okay? You are part of the system. Take the example of Earth. Planet Earth it has two different movement. One is called axial movement. Okay? And the other is rotational movement or circular movement around the sun. Okay, so you are not outside. If you were outside the solar system, you could see them moving extremely fast. But now you are part of the earth. You are standing on the earth. You don't feel the movement of the axis because you're already there, and the only thing which you feel is weather in day and night. Okay, so this rotating frame of reference can also be explained by called what is called merry-go-round or something.
Yes, sir.
Okay, so this thing I'm sure that you have seen them. There are a lot of different animals, and then children sit on them and they move very fast. So you see various uh, various object on which children are, are sitting, and it's moving very fast. So it's just you are outside it. So you don't really know what is happening. You can't even talk to your child or any one of them because they're just moving too fast and you don't really know what is happening. But if you jump over this merry-go-round, everything is still for you. You can talk to any one of them. And you know exactly which child is sitting on which animal. So this is the kind of system which is called rotating frame of reference. When you are part of the system, then you would be able to see the difference of velocity. If there are 5 different protons, and if you are standing on one of them, right on that needle, the 4 other protons The difference in them is only the differential velocity, the difference in Raman frequency, which is just in few hertz. Okay. So you can see them moving around. And this is the concept which was introduced, and that concept make life so easy because now you know exactly which proton is where. Atia, can you kindly explain this to the students now?
Yes, sir. So as sir explained you, I would actually repeat that's a very fascinating example for me as well. When just imagine yourself outside, there are two trains running that, as Dr. Iqbal mentioned, and both are very, very fast. So if you are just standing outside and looking at the two fast train moving, so you cannot differentiate the difference between the speed of the two trains because both are extremely fast, and it's just at a glance is going moving forward, but you don't know which one is moving little bit faster and which one is moving little bit slower. If you are in one of the train, and then you can see that if there is any difference, for example, as Dr. Iqbal said, one is moving with a speed of 300 kilometer per hour and the other is 301 kilometer per hour. So the difference between these two become only 1 kilometer because you, for example, if you are on the train which is moving with a 300 kilometer per hour, so that means the other one is with a speed of 301 kilometer per hour only has a one kilometer difference, and when you are inside then you could see, okay, this train is moving faster than the train you are in. So this is the concept because the vectors that we are discussing, all these nuclei, they are moving really fast with the speed of light. And when they are moving very fast and you are, and because you see the spectra, and when you see their velocity in hertz, right? If you convert in ppm and multiply with the frequency of the your spectrometer, you get the hertz. So that are only few hertz that you observe actually. Why few hertz? For example, if you take the example of 500 megahertz spectrometer or 300 megahertz spectrometer, whatever, these are the frequency of proton NMR. And when so it means each nuclei, each proton, not nuclei, each proton is moving with the frequency of 500 megahertz in 500 megahertz spectrometer, which is very fast. So, and why, and but there are difference because of the shielding effect, because of their chemical environment, their magnetic environment around these nuclei, they have some little difference. So, for example, one of the nuclei is moving with a speed of 500 megahertz, the other is moving with the 500.1 megahertz. So the difference is only 0.1 megahertz, right? But you cannot observe these when you are so standing outside. So as a matter of fact, the concept, sir, please correct me if I'm wrong. So your observer, your detector is also moving with this speed. So that is why the detector can observe the speed of each nuclei, each proton. Otherwise, if detector is not moving and standing outside, just as standing, so it means then for the detector, suppose detector is like you are a human being, so it is an eye. So it's very, very fast. So it's nearly impossible to differentiate between the speed of two protons, right? We are talking about proton right now, but this is the case for each nuclei. So it means the detector, that is the concept of rotating frame of reference. The detector has to move. Detector is an object like you. Okay, so you have to move, and you have to move with the same speed, like 500 megahertz. So then you can observe if there is a minor difference between the speed of different nuclei that we are usually observing in our proton NMR. You know, in proton NMR, you get ppm, like parts per million. So when you multiply these chemical shift value with with the speed of, or the frequency of your spectrometer, then you get hertz. So as a matter of fact, for example, some of you have solved proton NMR and you calculated the coupling constant, etc. Right? So these coupling constant are usually in few hertz, like 1 hertz or 2 hertz, 10 hertz. You know, these protons are not moving in hertz; they are moving in megahertz, but we are observing the difference in hertz. Why we are observing? Because the detector is a rotating frame of reference. So suppose these protons are in different trains which has the speed very different. There are several trains together, but very minor difference. So detector also has to move very fast. The detector is it has to move with the same speed to observe the difference. Am I right, sir?
Okay, yeah, so, Dr. Athiya has explained beautifully well. Unmuted? Yes, sir. Okay, so, for example, she gave the example of two trains. One is moving with a speed of 301 fast train, and the other is moving with a speed of 300 kilometer per hour. And assume that you are sitting in the train which is 300 kilometer per hour. So the difference is only 1 kilometer, but with time, remember that everything on the transfer plane is in terms of time. And you're trying to understand what happened in a particular time difference called delay, which we would study, that you would see after some time that your train is actually moving backward and the other train is moving forward. So after some time you would observe, though you are actually moving with the 300 kilometer, but in the rotating frame of reference, when you part of a reference, then your train is actually with time is going backward and the other train is moving forward. This is exactly what happened on transfer plane, that you have these vectors moving with the speed of light. Some are moving faster, a few hertz. Some are moving slower, a few hertz. And after some time, you'll see that one of them is moving forward, the other is going backward, because it is lagging behind. It's called lagging behind. Now, Dr. Adia mentioned that if you detector is fixed with one of the peak and moving with the same speed, then for the detector it's so easy to see where are the other vectors. But as you know, in reality, you cannot really move detector with the speed of light. So what actually happens is a simple mathematical equation that you subtract. When you're recording the FID, you subtract the operating frequency of NMR spectrometer, and that becomes so absolutely easy because mathematics are now conducted on few hertz of difference rather than on megahertz of difference. So it make life easy. But you see, more importantly, what is required for you to understand that only in rotating frame of reference you would be able to see the relative movement of these signals. If you're outside the frame of reference, then you will never be able to see that also. And this is desirable because in all NMR experiment, the modern NMR experiment, which has multi-pulse, multinuclear NMR experiment, you need to understand which peak is where on this three-dimensional Cartesian on this transverse plane. If if you do not really develop this concept of rotating frame of reference, you would never be able to understand that if you have three protons, which one is where and what is the location of it. And remember that NMR experiment, you need to play with them. The NMR spectroscopy is the play with pulses and with playing with the magnets, these magnetic vectors. In many experiments, which you will see after this lecture, you would be able to appreciate the fact that exact location of these vectors on XY plane is something so desirable for you to understand, because only then you would be able to give the second pulse. Uh, the second pulse experiment is something which will come forward, but at this stage, we wanted to introduce you to rotating frame of reference, and I hope that you would be able to read about it. I would recommend that whatever is absolutely impossible for you, that if you come to NMR class only and then you leave and then you don't read about it, you will never be able to understand. You have to spend some time to read about what was discussed today. And there are so many videos available, there are so many online lectures available which may help you to understand these concepts. These concepts are not difficult, but these concepts are so numerous. There are so many concepts that you need to understand in order to understand the NMR spectroscopy. Life was very easy when there was when there was a radio frequency absorption, continuous wave NMR. But all modern NMR experiment can only be explained by vectors, their position on XY plane, pulses which differentiate them, and then detector which record FID at different time intervals. And this is the second most important concept after the right hand thumb rule of pulses, where uh, radio frequency place them at different position on XY plane. Now, when they are on XY plane, all of them, if you have 5 different protons, they all are moving with the speed of light with the difference of velocity of few hertz, not megahertz. So it's few hertz that some of them are moving faster, the other are moving slower. Only you will be able to understand their relative position on XY plane when you are part of the reference, which is called rotating frame of reference. So you are sitting on one of them, standing on one of these vector, and then all these other vectors become almost stationary for you, and then you can see only the difference between them. If you are standing on a slower moving vector, you're actually lagging behind. With time, you're moving backward. And if the other are moving forward. If you are standing on the fastest moving vector, then you're actually moving forward, the other are lagging behind. And with time, which is called time delay, very, very important in and modern NMR spectroscopy, because the delay which you give before you give a next second pulse or open a detector is define where these vectors would be on XY plane. Okay, so this is a crucially important concept in NMR spectroscopy in order for you to understand what will happen after some time on the rotating frame of reference. Then you give a second pulse, and this second pulse, so many experiments thousands of NMR experiments are second pulse, third pulse, fourth pulse, fifth pulse, and literally hundreds of pulses. Uh, the one single pulse, which you have seen in case of a simple proton NMR or simple coupled C13 NMR experiment, is the easiest thing. And everyday things happen, but majority of the NMR experiment are not as simple. And for that, you need to understand not only when you give a radio frequency pulse, where the specters will go, but also you need to understand after some time they will split, and that their position on XY plane will be only understood with the concept of rotating frame of reference. Okay. Now, okay, now we start with the pulses. Let's play with the pulses. And as I said, the single pulse experiment is the easiest thing which you can do. But NMR are multi-pulse experiment, majority of them. COSY, NOSY, TOXY, HSQC, literally hundreds of these experiments are multi-pulse experiment. You cannot really explain them with single pulse. And this is what we intend to do. Okay. Okay, so we discussed that single pulse sequence is called sequences. It's very, very simple that you have this net magnetization vector. Now in children you give a 90 value pulse, it comes on X, you record FID. But multiple experiments are explained in this way, so preparation, you give a pulse represented by this particular rectangle, you record FID. Okay. But you can also have several pulses, so you can have this one single pulse experiment. This is the number of scales. So this is the simplest NMR experiment, which Dr. Atiyah explained, that 16 or 32 and you record FID. The easiest example for us to understand multi-pulse experiment is inversion recovery experiment, which is used for the measurement of T1 time, spin lattice relaxation time, but also an excellent demonstration of multi-pulse experiment. So these are two pulses, multi-pulse, and so 180 Y pulse or X pulse doesn't matter. Where the magnetization will go with 180 pulse, where the magnetization will go after 180 pulse. Tia, what is the response?
Minus E.
Minus Z. Okay. After some time, it has to relax back to plus Z through relaxation mechanism. And this is a longitudinal relaxation or T1 relaxation. After that, you give a 90 Y pulse and then you record experiment. This is the inversion recovery. So 180 pulse, it goes down there, you give a time delay, and as you know that during this time, this magnetization vector will try to go back to thermal equilibrium on plus z, and this time delay is adjusted. You have the capacity to change this time delay, incremented time delay. Okay, so for instance, 1 second, 2 second, 3 second, every experiment is different. And what happened with that? This is the representation. Okay, 180x pulse. People don't even write now. It's just the width of this is block. Uh, it's 180x pulse. This is tau, time delay between the second pulse. Then you give a 90x pulse, and then you record FID. It's so easy for you to understand. This is your M naught, longitudinal net magnetization, 180 X pulse or Y pulse, doesn't matter. It will come to this position, okay? And now you know that you cannot record that, okay? Because your detector is on XY plane. You give a tau, a time delay. In this experiment, let's assume that time is zero, So zero time, and then you give a 90 Y pulse. And 90 Y pulse will bring this to XY plane. You detect this one experiment complete. Okay, you record FID. In the second experiment, you wait for 1 second. Let's assume, 1 second. 1 second means that this magnetization vector will shrink because summer fill will relax back to Z. So the magnitude of this vector will shrink. And then when you give a 90 X pulse or 9 pulse, you bring it to the XY plane, and then you detect it. The third experiment, you give 2-second delay. This will further shrink. Okay. Then 4-second or 5-second. Eventually, what happened that after some time, this magnetization vector will be on the positive side, and when you give a 90x pulse, you would get this on a different phase. For instance, here, when it will grow up, then you see a positive Y pulse. FID would be recorded with a different phase, and you get this kind of a spectrum. So assume that you have so many different protons. When you give a pulse after 5 microsecond, you see all these peaks negative because your detector on the other side. And if the second experiment, this period is increased, you see relatively smaller negative peaks. Then several experiments, they're going to be one experiment where you see nothing because upper and lower peaks are same, that you have no signal, and then it start appearing on the positive side, and when you give a 90x pulse, you start seeing this signal increasing in size because they're going all the way up on this Z direction. It's called inversion recovery. You mean that you invert the signal 180, and then you measure the recovery in time domain. So minus from minus z to plus z, and you are recording this by 2 pulses. Every time you give a 90 pulse after a time delay, you see these vectors at different positions, right? And as a result of it, from full negative signal to full positive signal is T1 time. Now, this is what is called relaxation by spin lattice, T1 time. So this is used for measurement of T1, and you can see that for different type of protons, the T1 is different, because FID would actually measure them differently, but don't worry about that. The most important is this dimension for you. And this is the experiment which you need to understand to the core, because this is what eventually is the basis of multi-pulse NMR spectrum. It's called inversion recovery method. Uh, and this is recorded, and uh, often it is performed in order to calibrate NMR spectrometer. Also, for certain cases, T1 is very, very important. For instance, in MRI, T1 is measured. There are also experiment in which T1 is measured. But here, the objective of showing you this particular experiment uh, is to demonstrate what actually happened. So what happened is that 180 pulse invert the signal. This time, during this time, it naturally has to relax, and it relaxes, and every time you give a different delay, it is in a different magnitude, from minus z to plus z, from full minus z to full plus z is inversion recovery. And how would you record it? Only by 90x pulse. If you don't bring it to xy plane, you will not be able to record it. So it has to be on xy plane. And every time, after a certain time with delay, this is, if it is a negative signal, it will come right hand thumb rule -5. If it is a positive signal, up, then it will going to be -5. So you see from full negative to full positive. And during this time, uh, you have, now you should understand why it is important that NMR is multi-pulse. And second, that now you can see the position of these factors on XY plane. And with time they're inverting back to the positive point. Atia, you can explain this for a while and then you can show the.
Sir, we have a very short animation that Sumaira is going to show.
Okay, so I stop
Sir,
sharing.
yes, please. This very short animation that is helpful. for this.
Same here. So what made you select the shoe? Like
Sir,
Mhm.
sir, you may like to explain. this animation. So can you see?
Okay, so you see 180 xy pulse brought this magnetization vector down there. And remember that bulk magnetization vector is just a representation of several vector of the same direction. Okay, so then one 80 pulse bring it from z to minus z. Okay, now it has to recover, right? So you go from minus z to plus z, and in order to monitor this relaxation process, T1, you have to bring it to the xy plane. And remember the 90x pulse is 90x pulse, bring it to minus y when it is on the negative direction. But slowly, with every time delay, it will be on the positive side. From minus 90, minus z to plus z, you are recording various experiments with the difference of only delay, and that is critically important because then you know the position of that. It's not a spin echo, Atya. This is inversion recovery.
Inversion recovery system is.
Okay, so this is what is recorded, and you measure from full minus z to plus z by using the second pulse, and this second pulse bring it to xy plane. So you see from this umbrella is moving from full negative to full positive. Okay, and this as you seen in my slide, from full negative peaks to full positive. And remember, why full negative? Because your detector is on the other side. Remember the last time I told you that position of vectors on xy plane, uh, that detector can see them at different phases. So when it is on the opposite side of the detector, they all come on a negative detector. When it start detecting, they come as a negative signal. When they are just in front of the detector, they appear as a positive signal. So from full negative signal to full positive signal, this is relaxation process. And this relaxation process is measured by inversion recovery method. As I said, about 63 or 64% of relaxation takes place through T1 relaxation. So it is an excellent method of measuring T1. And this is also inversion recovery method is also excellent method through which you can explain the utility and importance of the second pulse. Okay. Now, my colleagues will explain to you about the probes, and the probe which they have in front of you is generally in the range about 100,000, so 100,000 USD. So the one which you will see in front of you is about $100,000.
So we are showing probe for 500 megahertz. Can you see this in the video?
I can see that. Yes, please.
I can bring it to the camera closer.
ये वाला कैमरा से दिखना है मैं इस वाले कैमरे को इधर ला
It's all right, Atya, you can explain it, please. You know better than me this thing. And okay, everyone, my colleagues will continue this presentation, and thank you. I'll see you next week, inshallah.
Allah Hafiz.
Allah Hafiz.
Yeah.
Okay. Don't forget, open the air. You know, it's very, very important. If you do not open the air and you put your sample in, it will directly go inside the probe and break inside the probe, and that will damage the probe. And that requires that is a waste of $100,000. So it's very, very expensive. And here, everything is there. You know, you have the detector and that Dr. Iqbal was talking about, and everything is just inside this probe. It's and all the pulses and how your sample receives the pulse and how it is recorded. So it is in these probe, and there are outside amplifiers and etc. things. But the main function, everything is just this small probe. And we have and we have other different type of probe. We have many probes, and you might look at the website of iccbs, then you could see we have various kind of probes. So this is one of the example, and your sample goes deep inside it. So, all right, can you see this? Right. So this here, this is where your sample goes in and sit in the probe, right? But it should not be without air bed. The air, because air bed bring it down slowly. So, and that's why everything that we are talking about is present here in this small probe. So it's very expensive. And this is what all about. You might, when you visit to an NMR lab, you might see it is in all magnets, there's a probe at the bottom. Okay.
And this is the NMR tube.
Yeah, that's an NMR tube that actually goes and sits
Inside
here
this.
inside.
Okay. And this is we use to adjust the sample volume so that it will be adjusted according to the probe head which you are using. If it is of 5 millimeter, you need to adjust it in a way that your sample should be having this volume. So after that, you open the airbag and then you put it inside the probe. It will go down and then you can start your experiment. Okay.
Any question?
I think this will be more clear when we'll show in the NMR lab visit.
Yeah. So do you have to visit now or next week? Okay, so we'll have a visit next week to NMR lab. Okay. Thank you.